Our next presentation is going to be Tyler presenting FRC design in the modern era.
Thank you. So I've been working on this for like the last 4 or 5 weeks. I'm really excited to do this presentation all day. If you don't know me, this is a very, very old picture. My name is Tyler Holtzman. I'm the design mentor for Pneumatics. I have been for the last while. In my professional life, I'm a senior design engineer. We build robots, we build automated systems for the food industry. 2010, been around for a while. I started as a student in the program way back when. And, yeah, still. So, a brief outline of what we're going to be chatting about this afternoon. So, what is the modern era of FRC? And how has robot design really changed significantly from even just 4 or 5 years ago? And what can my team do to improve on the field? So, what is the modern era? And the modern era was really defined by about 6 seemingly independent events. But 2019, Swerve Robotics released the Neo, a brushless motor comparable in size to the previous sim motor, which had been used for the previous 2 decades in FIRST. And the Neo came out and it was like double the power. And we had this kind of 2-tiered system where there were teams with Neos and you would watch their robot drive and they would look like unnaturally fast. And then teams that were still driving with sims. So 2019, Rev releases the Neo. Since then, several other brushless motors have hit the marketplace. But this was really kind of the first. The next really unique thing that happened was the kind of the proliferation of commercial off-the-shelf Swerve drives. So SDS, Swerve Drive Specialties, have been slowly building up their product portfolio. And the product was getting better and better and better. But in 2020, it really became widespread. 2018, the Limelight was released. And this didn't get the fanfare that it should have because, well, there was no vision in 2018. So they had developed this really, really cool product and released it, but it didn't really catch on right away. But since then, the Limelight has really kind of revolutionized machine vision in FRC. 3D printing and advanced fabrication that's accessible to all teams. 3D printing had been advancing a lot, but really from the period of 2018 till about now, you can buy Bamboo Labs X1C carbon for $2,000 that'll do what $400,000 Stratus printer did 10 years ago. So that kind of advanced fabrication that's accessible to every team has really changed the way a lot of teams are building robots. 2020, we also saw the removal of bag and tag. So prior to this, those of you who are around, we used to seal our robots up in big bags with a serial numbered zip tie and then write it on a little documentation form, and you wouldn't be able to touch your robot until you got to it. Well, that was really dumb. So FIRST got rid of it. And now teams can keep their robots and they can continue to develop all the way up until the end of their season. So this was a big fundamental shift in how robots are designed, the complexity of what you can achieve because you have greater accessibility to your robots. And then the last thing is the removal of the bill of materials. Prior to 2020, as part of your inspection checklist, all teams would have to submit a bill of materials, half the time that was written in Sharpie on a pizza box, of all of the components on your robot plus the costs. And there was a cost limit of $5,000 or $6,000 US at the time. But that is now gone. So these those 6 items are really what kind of fundamentally changed to move us into the modern era. So a quick look from the sim motor to a Kraken X60. We went from basically very restrictive motor rules where you were allowed 4 sims and 2 Fisher Prices and 2 window motors and 2 whatever else, to having unlimited brushless motors. If we compare and contrast the two, okay, 5,300 RPM, 5,800 RPM, okay, they're pretty close. But when we look at the P power, we go from 330-ish watts, so about a half a horsepower, to 2 horsepower. Massive fundamental change in motor power. We look at stall torque. So how much torque the motor generates when you dead stall that rotor. We're literally double. And stall current. We go from very high to unbelievably high to the point that it's not possible for you to pull that much power out of your back. So, oh yeah, and then the other thing, a sim motor with a motor controller, if you don't have an external sensor, you're like 3 and change pounds per rotary thing. And a Kraken X60 is 1.2, so you're like basically 2 pounds lighter per motor. Okay, you got 15 motors on your robot. That's 33 pounds of weight, which is an unbelievable amount for those of us that were building robots for a long time. 30 pounds is an unbelievable amount, to the point that like almost nobody hits the weight limit. So what does this add up to? Unlimited power. Not really unlimited power, but we have a ridiculous amount of power, more than we had 5 years ago. But it's not just like unlimited power. The Kraken X60's got built-in motion control that's way better than anything we could write ourselves, in the previous era, with a brushed DC motor controller and a potentiometer or an encoder or whatever that external sensor you were going to mount was. The built-in motion control on these things is unbelievably good, to the point that we don't use anything else. There's no reason to. Basically, all of the use cases of an FRC motor can be handled by velocity control, motion magic position, or motion magic velocity. Or just a regular old positional PID. So basically, the motors nowadays, they have all this stuff built in. Oh, built-in current limiting, that's a big one. And we'll talk about that a little bit later. And support for external sensors, whether it's limit switches or an external encoder or whatever that might be. So the motor technology we have is light years better than it was 5 years ago. So the next thing after, we have brushless motors, crazy motion control, we had also SDS in parallel developing Swerve modules. And now there are basically 4 competitive offerings that are all pretty similar performance-wise, from Swerve Drive Specialties, West Coast Products, Rev, and they all make very good modules that are comparable in their own right. Some have little pluses over another, but they're all generally very, very good. And championship last year, 256 teams in the elimination rounds, 254 of them used Swerve. So there was a time not too long ago where I stood up here and said, if you're building anything but a 6-wheel tank drive, you're doing something wrong. That time is long past. We are now very much firmly in the Swerve drive era, and if you're not on the Swerve bandwagon, you should. There is a significant cost associated with that, and that shouldn't be underspoken. But if you want to be competitive on the field in the modern era, Swerve drive is a must. So what did that mean? In the olden days, we used to devote a significant amount of our fabrication resources to building a chassis. We have all these robots on the rack that have fairly elaborate sheet metal chassis for tank driving. And we did that because we could kind of customize each one to the game. But now with Swerve, the chassis is like a joke. It's 4 stick tubes and a base plate. It's like you can make that with a hand drill in about 2 hours and have a chassis that's together and ready to go. So the fact that everything is pushed towards Swerve means that it's freed up a bunch of other fabrication resources for other stuff, whether that's mechanisms or programming or practice or whatever. There's a lot less effort going into building chassis now than there was 5 years ago. Robots are faster and more maneuverable. Like, it's very common for robots to be in the 12 to 18 feet per second range now. And 5 years ago, that was extremely uncommon. That would have been a unbelievably fast robot whipping down the field. So robots just generally go a lot faster now. Now, because robots go so much faster, we have much, much higher energy collisions. We're seeing frames getting bent and robots taking a lot more significant damage now than in the previous era, the olden days, so to speak. So we need to make sure that our robots are robust, both mechanically and electrically. So we're not going to break when we go downfield, and you hit corner to corner, your frame's not going to fold in. And our electrical system is going to be able to take those big hits. One of my biggest beefs with FRC right now is that the connection technology we have has not kept up with robots as they do. Like an RJ45 connector for Ethernet is not good for 100G impact. Like, that's just not a thing. And yet we have like a USB port with no strain relief just like stuck in the Rio, and all of your communication relies on it. So I'll get into it in a little bit, but we take a lot of steps to make sure that our electrical system is as robust as possible, and all of these sort of connection points that really aren't suitable for the types of loads that we're putting on them are able to survive. So a brief aside, how fast should my robot go? And you can ask a lot of different people this question and they will all give you different answers. For most teams right now, about 15 feet per second is kind of the sweet spot. Why? Well, a number of reasons. Acceleration and responsiveness. So if you have a robot that is approaching max weight, and you want your robot to be able to accelerate and respond predictably and repeatedly to the driver's inputs, you need to gear it in such a way that you're not going to overload the motors when you change directions. So 15 feet per second is slow enough that you have really good responsiveness and acceleration, and not so fast that you start to fall off the kind of torque curve of the motor. This is very much a generalization, and there are lots of use cases where a faster robot is better, and lots of use cases where a slower robot is better. So this is very much a generalization. Controllability. If you're going like 20 feet per second, your robot is going to be very difficult to control at low speed, simply because you have very poor low speed. So going significantly faster than this is going to make your job for controllability and drivability a lot more difficult. Current draw and battery life. I mentioned before we have basically unlimited power. Well, we don't really have unlimited power. We have a single 18 amp hour battery that we have to make last for 2.5 minutes. If you gear significantly faster than this, you will either A, have to current limit your motors so much that you start giving up performance, or B, start browning out by the end of the match. If you're a full weight robot. If you're lighter, that's a different story. But if you're a reasonably full weight robot, you will suffer current draw problems over the course of the match. Torque. We want to have a torquey robot. We want to be able to, hit an object or hit another robot and be able to follow through. The faster you go, the less torque you have. That's just a direct linear trade. And robustness. The faster you go, the harder you hit, the harder you get hit. So we want to be careful about making sure that our chassis aren't going too fast. We have a number of sacrificial frame numbers here. Power management. The current generation, current limits are a must. If we're going to stick 4 Kraken X60s with FOC control in our drive, and we're going to gear for 15 feet a second, we have to be current limiting. If we're not, we're going to be suffering significant brownouts and just absolutely killing batteries over the course of the match. So hopefully this is readable, but these are the current limits that we ran in 2024 on the tail end of the season. So one of the really cool things about the Kraken and the Falcon is that you can specify the supply current and the stator current separately. Now, if you're not familiar with that, the supply current is the current going into the motor controller. And that is what prevents the breaker on that motor from popping. The stator current is the current coming out of the motor controller going into the motor. And this is what directly limits the torque that the motor can produce. So you can play with these two values separately to kind of achieve the functionality that you want. So the way this works is for the supply current limit, if you were to exceed 80 amps for more than 2 seconds, it's going to limit the input torque or the input current to 60 amps per motor. In practice, we probably never ever had that condition true, and this is the only one that ever actually did it. That 90 amp current limit on the stator side of the motor is what does the majority of the actually limiting and preventing the really, really big current spikes that cause brownouts on your rear. So the stator current, if you're only going to do one, the stator one is the better one to pick. This one is a safer one to pick if you're worried about popping a breaker or something over a long term. But generally, the stator current limit is the one you want to set. And the faster you gear the robot, the worse off this gets. So this is what we ran last year. We may have bumped this up by 5 amps at IRI. But if you have a 90 amp stator limit, you're not going to notice any reduction in motor performance from the driver. But you do reduce those really, really big, really, really short, instantaneous current spikes when you change direction or suddenly apply. So in the modern era, we want to be having current limits on. The other thing to add in is we have a very, very aggressive rate limit on the chassis X, Y, and rotational velocities. So when I say aggressive, I mean aggressive enough that we're just filtering out the very, very large step changes in velocity. So our rate limit for X and Y was 600 inches per second per second. So if this robot has a max speed of 190 inches a second, or about 16 feet, if we have a 600 inch per second acceleration limit, that means the commanded velocity to the robot, if I were to jam the stick forward, would take about 300 milliseconds to go from 0 to full speed. So it's acceleration limiting the robot to filter out the really, really large step changes in velocity that are going to induce a large current spike that will lead to a brownout. And once your robot starts browning out, it's very difficult to recover from it because it will just kind of stutter and then brown out, and then the voltage will drop or will come back up, and then it will recover, and then you'll apply the throttle again, and then it'll brown out, and your robot will end up stuttering down the field. and that's no fun. So acceleration limits like this will help, current limits like this will help, but if you make these numbers too big, it will make your robot undrivable, and it will be sluggish and irresponsive to the driver's inputs. Because we can't hurt the drivability of the chassis still needs to be able to respond quickly to the driver's inputs. But the battery has to last 2.5 minutes. So we have this finite resource of power, and we need to manage that. So, chassis design. Chassis design has changed a lot. I mentioned about elaborate sheet metal chassis to 4 tubes and a plate. So they must be robust. They must have a low center of gravity. There's been a big trend lately to building small robots. Well, when you build a small robot, your support polygon, the area you have that's supporting you on the ground shrinks. And unless your center of gravity also goes down, your robot will end up being tippy when you drive around its speed. And if you want to go 15 feet per second around the field, it's ideal that your robot not flip over. So we must have a very, very low center of gravity. We want to be designing a chassis in such a way that it has flexible options for mounting mechanisms, bumpers, controls, stuff. And the kind of generic 4-stick tube chassis with a plate generally meets those requirements. This was the 2023 chassis. This frame member here suffered a catastrophic failure at the championship. Basically, it just folded in, sheared all the rivets away. So as a general rule of thumb, we support every frame member mid-span somewhere. We want it to be serviceable. If something does break, we need to be able to fix it. So this is the 24 chassis. So it had a 2x2 cross member across the middle. The intake side filled up this side, it's not really shown. But this frame member here had 2 big 3/8 plates backing it up right behind that were bolted to the bottom plate that would stiffen that frame member in the middle. And so that if this side took a big hit, that frame member wouldn't fold in. So generally speaking, 2x1 by 1/8 aluminum tubing is a great start for chassis. Commonly available. One thing that we have here in Canada that sucks is a lot of metal shops will try to substitute 6063 instead of 6061. 6063 is an architectural aluminum that has really good corrosion resistance. Nobody cares. But it's like 80% as strong as 6061, and it doesn't machine nearly as well. So if you can avoid 6063, I would strongly encourage you to. That being said, if somebody wants a bunch of 6063, I have some that I would love to get rid of. So 2x1 is a great start. The Rev tubing has like a pre-punched holes, but it's like crazy thin along the top wall. I would avoid that for your chassis and just stick to something with a good solid wall. They also have this like big scribe line down the middle of it that makes laying out holes really easy. That scribe line also induces like a huge stress riser when you take an impact, so your tubing can crack right along the scribe line. So just, if you're going to use that tubing, be careful how you use it in what applications. The last few years, we've generally stuck with a 1/8 aluminum belly pan. So this gives us a nice solid base underneath our tube chassis to mount electronics, to mount generally stuff. Back in the day, we used to do a 16th plate for weight reasons, but now you're very rarely up against the weight limit. So we do a thicker base plate. And if there's one part you're going to make heavy, it's the part that's an inch off the ground that is the entire bottom of your robot. You want the weight down low. You don't want the weight up high. So having a really heavy base plate is not necessarily a bad thing. A handful of teams have done like an 11 gauge stainless steel base plate, which is going to be about 3 times the weight So instead of like a 12-pound bottom plate, you have like a 36-pound base plate, which would be amazing. I would love to do that. But stainless steel kind of sucks the machine. You basically have to laser it or like zip cut it out with an abrasive saw. So that's not perfect. Consider battery placement early. The battery is the single heaviest thing you have in your robots. So once we figured out the general robot architecture, the battery is the first thing that we figure out where it goes. So 2023, we had the big arm that reached way out. So the battery was right in the very back because we wanted to be stable when we were reaching way out in front. So we stuck the battery at the very, very back of the chassis. You want to think about ballast. Because we have all this extra free weight, because of our brushless motors that are crazy light, you have the flexibility to put ballast in your robot strategically to make it handle better. Generally speaking, a robot that has the center of mass as close as possible to the turning center of your robot will handle the best. And the turning center of your robot with a skid steer drive would traditionally have been stacked out in the middle. With a swerve drive, we can actually arbitrarily define the turning center of your robot however you want. So this robot, the turning center was not actually at the center of the wheels. It was shifted about 2 inches forward to be under the center of mass and centered on the robot geometrically because the intake stuck out the front. So you can play with the battery, you can play with the ballast, you can play with all these things to try to improve the weight distribution of your robot to improve the drivability. There are a lot of other things you need to do, like score points before you start worrying about drivability. So don't spend a ton of time on this, but put a little bit of thought into where your battery is going to go. Because it sucks to try to jam a battery in like some weird place after you've got the robot together, especially if that really hurts your weight distribution. Support all frame members mid-span, I touched on that. Yeah, getting your frame bent in sucks. Build your robot strong. So yeah, there's a 2 big 3/8 plates right behind that, and you can see them on this thing at the front if you come look at it. We want to make sure that our robots are robust electrically. So, especially in the modern era, robots are taking hits harder and harder. So we want to make sure that we're securing our wires and cables as robustly as possible. That's our new radio bracket for the new radio. It's a 3/16 aluminum plate. And then there's these two little 3D printed blocks right behind here that have little saddles and tie wrap holders in them. So we're holding the Ethernet cable right by the base of the connector and tie wrapping it jammed into the radio so that even if you grab that cable and reef on it as hard as you want, that thing is not coming out. And we do something similar to this on basically everything now. The Kraken motors, you can't see that at all. We 3D print a little housing that covers the back of it that keeps the wires tucked in nicely, that stops any kind of debris from getting close to the motor terminals. The one that it comes with has got kind of open spots, and especially with Swerve where your motor is upside down, like almost above the ground, it can end up picking up debris from the carpet, whether it's metal shavings from somebody else's robot or a bolt or a chain link or whatever. If something gets up into that motor that's riding an inch from the ground and hits your cam wires, your whole robot's toast. So we print this little housing that covers this all up and keeps that enclosed. And it's got a little notch on it right here so you can wrap a tie wrap around the whole thing and clamp those cables down to that motor. And it's just along with 2 little screws on the existing terminal. Generally, for all our CAN connections, we solder and heat shrink everything. We don't use any crimped connectors for CAN. We strip both ends, spiral wrap it, solder, realize that you forgot to put the heat shrink on, cut it off, do it again. Yeah, solder and heat shrink everything. Robust battery mounting. Now that you've figured out where you want your battery to go, make sure that it's gonna stay there. Robots get hit really hard, and your battery is your heaviest thing. So you wanna make sure that the strap or whatever it is that's holding your battery down isn't gonna break and send your battery flying out of your robot. Hot glue, USBs, and PWMs. For anything that we can't strain relief with a little 3D printed thing, we'll hot glue the connector in. So all of our like PWM ports on the Rio or the USB connections to the Rio, we'll put a dab of hot glue on the back. Neat and tidy wiring. Generally, you want to have your wires in nice, neat little bundles that are tie wrapped down every 4 to 6 inches so that you don't inadvertently snag one with your hand while you're maintaining something or working on your robot. You want to have stuff tied down, nice, neat, and tidy. You open the cover on your robot, you shouldn't have this like massive wires that you have to push down. And this just really comes down to leaving enough time in your schedule so that you get your robot together, you can devote a couple of days to making sure that your wiring is nice and neat. And a torque wrench for screw terminals. How tight is too tight, or how tight is the correct amount of tightness, is an age-old question that students have struggled with since the dawn of time. CTRE has their own little torque wrench that comes with the correct bit for the Torx fasteners that come with that motor that is set to the correct tension. So I recommend that you buy the little $10 torque wrench and actually use it. How much is this? $40. $40.
30 US.
Afford that. Pneumatics. Reports of my death are greatly exaggerated. There's a lot of debate. The majority of people in the community seem to think that pneumatics are dead. I would disagree with them, mainly because while we have this unlimited, incredibly powerful motors, now we have this battery that is limiting the amount of available power to you over the course of the match. And pneumatics give you an additional power source other than the main battery that you can pull from over the course of the match to do simple stuff. If you have a simple two-position mechanism, or a little clampy thing, or a hanger that goes up and down, very simple two-position mechanisms can easily be accomplished with pneumatics. And once you get familiar with pneumatics, there's lots of neat little things that you can do with them if you have a little bit of experience. So our hanger last year was on a single solenoid, which meant that we would energize the solenoid to lift the hanger up, and we would de-energize the solenoid to bring the hanger down. The nice benefit of that is at the end of the match, when the power is cut to the robot, that solenoid will shift automatically. So the hanger will come down at the end of the match, whether we command it to or not. So with 2 seconds to go, we can be shooting our last game piece, driving backwards to the chain, hit the chain with 0 seconds to go, our power to the robot gets cut, the solenoid shifts back to neutral, and the hanger goes down, even though we have 0 time left on the buzzer. And we've essentially bought ourselves an extra 5 seconds per match to not have to be lifting ourselves up while the timer is running. So you can do some cool stuff. Unique products. Now, you are going to use pneumatics. You need to make sure that you have mounted them in a robust and protected manner. This was a match at IRI a couple of years ago. There's a collision down here between 1023, who mounted their accumulator tanks like right on the back of the robot, and I think 5712 hits them with their intake out. And I'm standing just off camera here, and I got hit by a piece of the tank when it exploded. So you can see the whole field crew jumps back, but that tank exploded into a billion pieces. So maybe don't put them on the back corner of your robot where they're going to get hit. We color code our pneumatics. Red retract, blue extend. So blue extend, red retract just makes things a little bit easier for tracking down. Other little tips that we have. I kind of stole this from my 3D printer, but we make little clips like this that go behind the push to connect fittings. So you push the tubing in, and then you print a whole whack of these little clips, and then you shove that in by the little collet behind it, and then that stops that from accidentally getting depressed in a tube coming out. So it's this little thing that takes like 4 minutes to print that you jam on your fittings that's going to stop that tube from coming out inadvertently. The other thing is you can get these little tubing cutters from Amazon for about $10. They have a little V-groove notch in the bottom of them that holds the tubing nice and square, and a real sharp blade that will cut the tubing nice perpendicular angle so that when it goes into one of these push-to-connect fittings, you get a really good seal, no leaks. So I strongly recommend teams get these tubing cutters and use them if they're going to use them. Similar to wiring, we want to make sure that our plumbing is neat and secure, and we're not going to have a tube get snagged on something and have somebody rip out our air. So we had this big monster air tank in that robot, and we would actually just disable the compressor the whole match. So hanging wasn't a huge thing last year in terms of points. Hanging was really important to earn the additional ranking point, but in terms of actual points, it really wasn't worth all that much. So we would charge the robot before the match, and then disable the compressor completely until the driver hit the hanger up. So even if we had a catastrophic loss of air pressure, the compressor is not just running the entire match. And we had enough stored air on that robot to hang twice if we missed the first time, without the compressor running at all. So we're basically just carrying around this big energy store until the very end of the match, and then we use it. If we had smaller cylinders like the gripper we had in 2023, we probably could have ran the entire match with just that cylinder storing our air and not run the compressor. Now the rules say you have to have the compressor on your robot. They don't say you have to actually enable it. So we run the compressor in the pits when we're doing our pit checks, and we charge the air up, and then just leave. No leaks. So our goal is always less than 5 psi loss of pressure per day, which is pretty good. If you take your time and you check for leaks and you make sure you're using the tubing cutter, you can get a robot that will hold air for like weeks at a time. If I go back to the shipping era, we once shipped our robot to the Waterloo Regional. We took it out of the robot 4 weeks later, and there were 80 psi. So it is definitely possible to build a robot that does not lose any air. And that one generally loses about 5 psi. So we could charge it the night before and go up to a match the next day, and we can just. So pre-match, post-match, we want to be doing preventative maintenance. We have a little routine that we run through when we come back from every match or before we go to every match that just verifies all the machine functionality. We take the drivetrain, we run it forwards, backwards, left, right, spin in a circle, run the intake, spit the note out, run the intake, spin the shooter up, go up to the amp position, bring the thing back down, wave an April tag in front of it, wave a note in front of it, put the hanger up, put the hanger down. Basically, we go through all the functionality and make sure that everything works. And we do that before and after every match. You want to be doing visual inspection, you want to look, listen. Quite often, your robot will make a new sound. That's usually something's funky we need to figure out. So I always tell kids, the robot will talk to you if you listen. So listen for new and exciting sounds that you've maybe never heard before, because they're probably a sign that something is wacky and about to fail or loose or needs attention. Fresh battery, charged air. Robots are so power hungry now, if you're not changing your battery every match, you're in for a world of hurt. So make sure you have fresh batteries every match. Make sure your battery leads are tight. Make sure that you're not using batteries from 2015. We pretty well buy a new set of batteries every year, because the cycles that they go through where you're draining them very quickly to a very low level and then charging them all the way back up again. They're very hard on the battery's life cycle. So we generally only get about 1 year out of some batteries. Periodic passing check, just make sure stuff's not coming loose. And make this a routine process. So you're doing this every match before and after. So that's been a lot on brushless motors and swerve drive and chassis design. Are there any questions on this? Yes.
How heavy is the spot, and then what is the speed?
We're 124 and change, so we're basically right at the max limit. And we were L3 gearing, which works out to about 16 and a half. And we had a big debate whether we were too fast. Early in the season, the game revolved largely around full field cycles, racing down to the human player station, racing all the way back and scoring, down to the human player. So early in the season, being fast was an advantage. As the season progressed and the kind of passing meta emerged where one robot would be down at the human player station just passing notes, just chucking them down the field, where they were only driving at about 10 feet. You could have geared your robot for 12 feet a second, it wouldn't matter. You're going to be just fine down there. So early in the season, being faster was better. As the season progressed, it mattered a lot less. So yeah, we were L3. We were probably, I thought we were too fast. But we also needed to win the race to the midline, and you need to be fast for that. So for this game, L3 was about good. If we were to do L3 again, I would want to be like 15, 20 pounds lighter. Because we did have to current limit substantially to not bring.
Do you remember when you were for last season, like charge shot?
We were 10, 15 pounds under, and we were L2 gearing. So we were 14 and high 14s feet per second, and this year we were mid 15 or mid 16s. More questions? Yes.
You said how you soldered while you can like wire thread.
Yeah.
What was the connection into the wheel?
So that one you're stuck. You're pretty well. You got to trust that wheel Mueller connector is going to hold. So we ferrule ours. So strip it, crimp the ferrule, put it in there, give it a good tug test, and hope for the best. You can hot glue that one too, but then if you ever got to get it out, it's like kind of sketch. But we do tie wrap that cable off right beside where the Rio is. If you want to come have a look, we 3D print these like little stands on the four corners of the Rio where the cable is strain relief to, and then it just like tucks right in. So it's not going to get snagged and yanked out. Now, if that crimp's bad to begin with, then yeah, it's a bad crimp. So,
They don't use like a mechanical or anything.
we do use a chemical. Yep.
What's your plan for in case let's say a can wire breaks somewhere along the line? What's your plan for fixing that? Like using a like a Wigo, or is it like solder back?
Well, the plan is to not break in the first place. We take a great deal of time to make sure that can cable, which is mission critical for the robot, is as robust as possible. But yeah, there's no quick fix for a broken can wire if you don't know where it is in the bus, because it could literally be anything. So the best way to approach that is from a preventative aspect rather than trying to band-aid it after it breaks. You got to make sure that it's 100% rock solid the first time. Yes.
Do you continue with little kind of experience to try and make that jump through the season, or are like servos good enough?
Servos are better than they used to. If you've never done it before and your team has no experience with it, then I would not take it on in the season, because you don't know what you don't know. And you're not going to find out what you don't know until you try it. But if you try and fail, then you're finished. So do it in the fall. Do a little workshop where you make something with pneumatics. Make a little catapult that flips balls up, or make an intake that deploys in and out with pneumatics. Do something like that to gain some experience, to gain some exposure to pneumatics, and learn the things that you don't know. That's really the trick to, well, pretty much everything in life. But you don't know what you don't know, and until you do it, you won't try it. But it's also a big risk to do it in the season with something that's critical to your performance. So do it in the fall, play around with it, learn the things you don't know, and then execute it. Yes.
Any reasons to use PWM over CAN, or other than some like firmware issues or other issues?
So the question was, is there any reason to use PWM over CAN?
Like a specific motor or something.
No, not anymore. Back in the day, yes. But nowadays, like, if we lose the left shooter motor, we're pooched. If we lose the shoulder, we're pooched. If we lose the drive motor, any single failure on the robot, we're pooched. So trying to design in redundancy for individual things, if it ends up costing you more effort to do, you're still pooched if you lose the motor. So you might as well just put them all on can, put all your eggs in that one basket, and make sure that it's 100% rock solid. Yes.
Do you run the whole can loop on the can board? Or do you have 2 can loops?
We have 2 can loops. One of them is the Rio, the PCM, and the power distribution panel. And then the other one is every other motor and encoder.
And that one goes into the can board?
Yes. Yes. Now, part of the reason behind that is we use the CTRE Pro whatever, so you have to use the can board in order to get that functionality. You can't put a Falcon on the Rio bus and then use the CTRE Pro functionality. That's okay. More questions? Yes?
Does it overload the can board?
No, the amazing thing about the can board is it has like 10 times more bandwidth than the Rio can loop. So you can put as much as you want in there, you're not going to overload it. Unless you try to run it at like 1,000 hertz, but there's no reason to do that. So the can board is amazing. It solves all of those problems.
Do you also ever change the times?
Generally, no, we stick to the 20 milliseconds. More questions? Okay. Vision, 2018, Limelight released the Limelight. And it was a real shame that 2018 didn't have more stuff to do with vision. You could basically just do the entire game challenge with odometry, which is what almost everybody did. So the Limelight, which was this phenomenally game-changing product, was released, and then like hardly anybody used it until the next year, 2019. So Limelight came out, and they had this canned vision solution that could do retroreflective tracking, which is what pretty much everybody used at the time for tracking goals, tracking game uses, tracking stuff. And that basically made vision easier than ever. Before that, we used to get a Microsoft webcam over USB with a 3D printed ring light, and then like hack in some terrible vision code that ran on the Rio at like 3 hertz that was not fast enough to be really overly usable. And now we have this like 90 hertz off-the-shelf solution that you just stick on your robot, 20 minutes, it's set up, and it's ready to go. So nowadays, we have, the latest is the Limelight 3G that does really good equal time tracking. It can do full like 3D positional estimation that's pretty good. It'll do 2D tracking extremely quickly. The Limelight 3, if you plug Google Coral into it, will do machine learning, object detection. You can detect a note versus whatever, or just do some color tracking, look for an orange blob, or a yellow cone, or a blue cube thing. So Limelight is super awesome, and it really changed the game in terms of machine vision. Nowadays, there are lots of other solutions. There's Photon Vision, which is kind of this crowdsourced, open source, bring your own hardware platform, put our software on it. It's kind of cool if you want to try to roll your own kind of solution. Whether you use one or the other, consider your team's goals and resources and budget and all those things when choosing one or the other. Limelight is super easy. It is not inexpensive. They're $300 US a piece. So there's a significant cost investment there, but there's also a big time savings there. Yeah, time, effort, reward. Reliability. So 3D printing and advanced fabrication has really become a lot more prevalent and a lot more accessible in the last few years. We've got websites like FabWorks, Ready, Set, Cut, CutMyParts.ca, SunCutSend. These guys, you upload a CAD file to their website. They give you instant quoting online, and you could just like, here's all my sheet metal for my robot. It's $600 and I'll have it in a week. Like, and now this is something that every team now has access to. They can just like order the whole sheet metal for my robot if you have budget to do. And because the bill of materials and the cost cap is gone, you can just do whatever you want. So we have all these resources now that have made advanced fabrication accessible to everyone that can afford it. And we've got companies like Bamboo Labs that are making incredible printers that are incredibly capable, that you can do unbelievably strong 3D printed parts in pretty much whatever shape you want, that are accessible to all teams. So there was a time not too long ago where the ability to make your own gears was an advantage. And nowadays, well, everyone just buys gears, but you can print a gear, a plastic gear for a low-load application, or you can print a sector gear for the back of your shooter hood that's a very, very complex geometry that previously would not have been possible to fabricate on an FRC team. So advanced manufacturing has become much, much more accessible, and robot design has moved on accordingly. So the other big thing in the modern era is no more bag. So, back in the day, we would seal a robot up, we didn't have any access to it. So for us, we still build two. There's still a lot of advantages to having two, even though we don't have to seal the one up anymore. We can be doing autonomous development on one end here while we're upgrading the shooter on the other one in the hall. We still use both all the time. We maintain both all the time. And the practice robot, they drive the snot out of it all day long. And then this one stays kind of in pristine shape for competitions. And anything that comes up along the way on the practice robot, maybe there's a reliability problem, or maybe there's a belt that wears out, or maybe there's a screw that continually comes loose. We can identify it on that machine and then correct it on both before it ever happens on this one in competition. So when we get to competition, we're sure that the machine is in a mature state where we're not going to be learning that the belts break if we do X, Y, Z. We have a very stable platform, and when we get there, we're there to play. We're not there to learn what's going to break on our way. So the bag didn't really change our approach to build. The one thing that sucks about no bag is the season is very long. Instead of meeting Monday, Wednesday, Friday, Saturday, our 6-week in build season, now we meet Monday, Wednesday, Friday, Saturday until championship. So the season is very, very long. So we need to be aware of burnout as the season goes on, with students missing time, mentors missing work, people being away from their families. We need to manage that carefully and take days off when it makes sense to take days off. So no more bag meant we have nearly unlimited access to our robots, which is great. But it means that the value of having access to an accurate practice space has never been greater than when it is right now. When we used to have to seal our robots up, there wasn't such a big divide between the teams that have a practice field and teams that don't. But now that you can keep your robot out, you can be driving 5 days a week, or 6 days a week, or however much you want to drive. Whereas before, when we used to have to seal our robots up, you couldn't touch them unless you had 2 robots. So the fact that we have no more bag now has made access to a practice field more important than it ever has been. And there's no more bill of materials. So before 2020, your bill of materials, you had a finite dollar cap of $6,000 budget. If you had to cost account for 20 Krakens and 2 Limelights and a Cannibore and a Pigeon and all the commercial components that are on it, we'd be well beyond what the budget cap is. So the fact that the BOM has been eliminated has really unlocked a lot more ceiling for robots to be developed. And we see that on the field now. The robots are just a lot more capable and competitive than they were 5 years ago. It looks like we're playing a different game than we were back then. So we still do have the $600 US component limit for an individual Swerve module or a camera or whatever. But yeah, now you can just ball out with Krakens everywhere instead of having to put a window motor in somewhere because you're going to be up against the budget cap. So this is where it all kind of comes together. The bomb, getting rid of the bomb made 8-motor brushless Swerve drives possible because you're not up against the budget cap. The advanced brushless motors, the motion control, made Swerve drive easier because now we have this amazing closed loop motion control that's super, super easy that makes Swerve drive a whole lot easier. There's a whole whack of published Swerve libraries. So the initial investment to get Swerve, it's not just like you buy some modules and then spend 30 weeks coding them. You can grab CTRE's Swerve generator and be up and running in 30 minutes. No bag allowed for greater development time. So teams are, they have more access to fields. They have more access to develop the robots. They have more access to do more things. And the decreased weight of brushless motors has freed up like 30 pounds of weight budget that we would not have had in the previous era. Oh yeah, and we got crazy cameras that make vision like almost trivial. So what does it all mean? Robots are faster and easier to build now than they ever did. The fact that we can build that thing in 3 weeks and have it running by the end of week 4 and driving around is crazy. But teams have access to advanced fabrication that's quick. You can get a robot together running fast. You have more commercial off-the-shelf components now. You can just buy a bunch of stuff and stick it together. You don't have to spend weeks and weeks and weeks designing and fabricating custom stuff. Advanced control, easier than ever. You no longer need to have advanced manufacturing to be ultra competitive. We still use our sheet metal sponsor. We still use our tubing laser sponsor. But we could make that stuff in-house ourselves if we really, really had to. It wouldn't be as quick, but we could still do it and it wouldn't put a huge dent in the schedule. Reliability and robustness is more important than ever. Robots are generally more competitive, generally more reliable. So we can't afford to be sitting dead on the field because we had a can wire. And this unlimited, ultra lightweight, ultra powerful motors has given teams an extra 30 pounds of weight budget. Now, when teams have an extra 30 pounds of weight budget, the tendency is to keep adding more and more and more stuff until they're up to the weight limit. When adding more stuff is not always the answer. So what now? Leverage costs where it makes sense. Some teams like to build their own Swerve modules. I don't know why. You can buy something that's going to work just as good as you can possibly build. So if the goals of your team are to build a Swerve module because I want to train my students in advanced manufacturing, great. That's a great reason to build your own Swerve modules. If your goal is to be competitive on the field, you should be buying your Swerve modules. Unless you can't afford them but have advanced manufacturing resources and the time to do it. But generally speaking, we should be leveraging commercial off-the-shelf parts where it makes sense. Be robust. I can't stress this enough. It's really uninspirational to have your robot dead on the field. So build your robot robust. I always talk about this, designing and building within your resources. My other presentation this morning, I talked a lot about that. It takes a great deal of knowledge, experience, and maturity to say, this is too much for my team and I need to take a step back. But doing that will often save you a lot of heartache later on in the season. Don't neglect the programmers. FRC is becoming more and more a programming competition and less a robot building competition every year as more stuff gets released. So don't neglect your programmers. Leave significant time on the back end of the season for programmers to have time with the robot to develop stuff. practice, practice, practice. Don't give the programmers all of the time, give them some of the time, as much as they need. But practice, practice, practice makes a big difference. Do less better. Most teams overreach. They try to do too much. They end up falling short of what their potential was had they scaled back ambitions and done less. A brief case study on the trap. Those of you who are familiar with last year's game, the trap was this extra scoring challenge where you had to drop one of the notes in this little chute that was up on the stage that you could only reach while you were hanging off the chain. And the size limits of the robots were such that you had to like lift the chain like almost to your bumpers and be like perched on top of it in order to drop the note into the little slot that had to go into. And it was probably the most mechanically difficult game challenge we've ever had in FRC. The fact that you had to be like perched on the chain, but reach up really tall and drop this thing in, but also have your robot be small enough that you can drive underneath the stage. And you still had to be good at shooting because like 95% of the game was shooting notes in the goal. And the trap was this like tiny percentage of points that you could earn other than the fact that it was the potential to earn an extra ranking. So 99.9% of teams should not have attempted the trap. They should have just completely ignored it flat out. A lot of teams, the majority of the ones that trapped, should not have done this and would have been generally more competitive when they ignored it completely and just shot in the speaker and and the reason why is designing your robot to do that is going to compromise the entire rest of the architecture in order to do that. And the teams that just flat out ignored it were, it's a vastly easier design challenge. If you just rule that out completely and just worry about the amp and the speaker, you're way better off. The 5 points that it was in a match wasn't even worth doing in an elimination situation because 5 points is a single amplified note in the speaker. And there were other combinations that allowed teams to achieve the ranking point. If you had 2 hangers on one chain and 1 on a solo chain, you could get the ranking point with no trap. If you had 2 on a chain with spotlight, that was enough. There were other ways that you could do it without scoring the trap at all in order to earn that extra ranking. So for all of these reasons, I think the majority of teams should not have attempted the trap. And the teams that should have attempted the trap are only ones that came from the regional system that had to seed number 1 to win some ultra competitive regional in California because that is their only path to challenge. So there is a handful of teams that should have trapped and had the resources to do it without taking anything away from their ability to score in the speaker and the amp, that it was actually worthwhile. Do less. Master the simple stuff. This robot here, there's nothing overly complex about it. There's a lot of complicated things that you can do in FRC, whether it's machine learning or 3D bot pose or multi-jointed arms or elaborate elevators and note paths that can allow you to do all this stuff. We have a single pivot to score in the amp or in the speaker. We used the off-the-shelf limelight solution to track an orange blob for our note tracking. That enabled us to pick up notes along the midline in auto. That enabled the driver assist for the robot will kind of automatically steer itself into a note when he's picking up. And the color tracking took us like half an hour to set. We spent a couple hours on the algorithm of how to steer the robot into the note, but the actual like vision to find the note and where it was in the field of view took like a half an hour to set. Versus a machine learning solution, which is going to take significantly more time and probably not perform as well anyways. Along the same note, we only look at the single April tag beneath the speaker. There were lots of teams that were looking at all the tags on the field at the same time and calculating the robot's position on the field and then using that to shoot in the speaker. And it wasn't accurate enough to hit the like 1 degree of tolerance you needed there anyways. Or you're going to drive all the way up to the speaker and then you're so close that you can shoot blind anyways. So why the 3D box? We look at the 1 April tag, we use that to snap the heading of the robot. We have a very simple limelight TY to distance lookup table that approximates the distance from the goal, and that's what sets the shooter angle. And that allows us to shoot basically out to the window. So we have this very simple approach that was reliable and robust for us and worked better than a much more complicated approach. We had this dead simple pneumatic hanger that just went up and down. And lots of teams had these elaborate winches that would pop out, swing up, and hook on, or whatever else. It was a hook in the middle of our robot that would go up and down. And we could hang anywhere along that chain and it didn't matter. And despite the fact that we completely ignored the trap altogether, we still see the number 1 at every event, with a 3.5 ranking point average across the season. And only lost 3 matches. Fortunately, 2 of them were on side. So, some heartbreak there. But generally speaking, I couldn't be more proud of everything that we accomplished this year by doing less better. Thanks to our sponsors. No question. Yes.
Do you have any tips for optimizing robot geometry in CAD? So that how do you know when you're done?
How do you know when you're done? Well, the first thing is you're never done. But there's a certain point where you get to good enough, and then you start building. How to set up geometry. In what sense do you mean set up geometry?
Like when you see your length of your arm across you.
Okay.
How do you what is your use to set up your geometry there?
So in that case, we'll draw a 2D sketch on a plane with a chassis, and then we'll draw in the relevant geometry of the amp or the speaker or whatever else, and then we'll just draw in boxes that represents, okay, here's a box that represents this tube with a point, it's the pivot point for the shooter, and then just draw in a little T-shaped thing and then kind of pivot that sketch around and line it up in such a way that it looks like it's going to go into the chute. And we'll kind of do some very quick, just 2D sketches on a plane to scale in SolidWorks with real dimensions and reasonable space claims for stuff. And then play with that geometry and see what it's going to look. When we initially came up with this architecture, I thought that we were going to have this on an elevator that actually went up. And then Balraj went back and laid it out and said, hey, if we just move the pivot a little bit up and forward, we can achieve what we want with a single pivot and no elevator at all. And I said, great, let's do it. And then we figured out that, if we put a 10-inch stroke cylinder here and we tip it back just a little bit so that it clears those intake rollers, we can jam the hanger in right on top of everything, and it's going to fit just fine. So we really just make a 2D sketch and draw in like a side view of what the robot's going to look like and play with that geometry until we get it looking pretty good. Now, it's tough to visualize a whole robot when you're just looking at a 2D sketch of one plane of it. So the more experience you get as a designer, the easier that will be to visualize and go from a 2D side profile to what the thing will look like in 3D. What some teams will do is they'll draw kind of a block, kind of dummy model. They'll make a chassis and just extrude some tubes and make a very simple, like 1-part block model of what the thing is going to kind of look like. And that works for a lot of teams. We like the 2D sketch approach. It's a lot easier to visualize and convey your ideas to others if you can draw a little 3D sketch or 3D kind of mock-up of what the thing's roughly going to look like, even if you don't have every part and every nut and washer and shaft modeled in. Just draw some cylinders that represent your wheels and make a little T-shaped frame that represents what your shooter's going to look like. And then just put a pivot and maybe to a hole or something so that you can play with that geometry until you figure it out. And you can download a whole CAD model of what the robot field looks like now on Kickoff. And then you can plunk your robot down in the field and line it up with the amp and see what it's going to kind of look like, in the CAD world of the real world. So, yeah, 2D sketch, simple 3D model, whatever works for you is best. Yes.
At what point in the season do you determine your chassis size?
Fairly early, like Wednesday, Friday. We are very, very slightly longer than we are wide. And that was, we had to do that to get enough room for the note to come up off the ground and come into the shooter and have a little bit of clearance here so that when this thing goes through its range of motion, it doesn't come too far outside the frame perimeter. The whole end of the shooter changed a little bit after we built it. The first one was not very good. So this actually does come outside the frame perimeter a little bit, but it never really comes beyond the bumper perimeter. But fairly early on, like the chassis is usually more or less at the end of week 1. So the size, unless we have a really good reason to change it, is usually driven by that.
And by that date, do you order just chassis parts then?
Well, I mean, the chassis parts are 4 tubes, which are on the shelf right now. There's a base plate that goes out with the sheet metal order, and then 4 Swerve modules, which you should have before the season anyways. So chassis design, not like you have to order a bunch of gears and wheels to build whatever you want. Like the structure should be sitting on your shelf, and the modules, now are robust enough that you can reuse them year over year over year. So you shouldn't be ordering Swerve modules in week 1. You should have those on your shelf already. Hopefully in the right gear ratio, which is why generally most teams should go about 15%, which corresponds to the L2 ratio if it's SDS, and I don't know. More questions? Yes.
How do you deal with like different wear and notes?
How do we deal with different wear and notes? We chuck them all so hard that we don't care. And that's pretty much the answer, to be honest. Yeah, our shot is the same speed whether we're up close or all the way back at the wing line. And we just huck them really hard. And it's the bad notes at the wing line will miss. And that's just, from the wing line, you have like a ½ degree window to actually make that shot. So just don't shoot bad notes from really far away. And generally speaking, at higher level tournaments or higher pressure situations, we have good notes anyways. Like if it's DCMP or if it's championship, the notes are pretty good. More questions? Yes.
So I know in your previous talks you say you guys have kind of like your design done by the end of like the first-ish week roughly.
We have the architecture.
So do you guys do like prototyping between just to kind of like figure out how much compression you need on the notes and stuff, or how do you guys figure that out usually?
So we prototype as necessary. And they're usually very, very janky prototypes to figure out very, very specific things. Like the height of the 2 rollers on the intake to pick the note up off the ground, but not apply too much downward pressure that it doesn't slide across the carpet. So we built a mock-up of 2 rollers in a piece of plywood with 2 cordless drills to figure out what geometry we should use. And then when we're designing, we're using that geometry in the CAD. But we're not building elaborate prototypes of moving wooden robots with a whole mock-up and everything. We spend dozens of minutes on prototyping very, very specific things that we need to determine empirically that we can't derive just from the CAD model or drawings or previous experience. More questions? Yes?
So what tone do you use?
I'm glad you asked that. I could give a whole talk on 3D printing. So we use the nylon carbon fiber from eSun. It's what I like to call poor man's Onyx. It is about $50 a roll, and it's the best nylon carbon printing filament that I've found. There's 2 Canadian distributors for it, Matter Hackers and 3D something or other. If you Google it, you'll find it, UPACF. It is very difficult to print. Out of the bag, it's unbelievably wet. So you have to dry it brand new. My recipe is 12 hours at 90 degrees Celsius in an oven. And then if you're gonna store it in a sealed bag with a big wad of desiccant. And the generic profile from bamboo works remarkably well when it is dry. If it is not dry, it prints like dog food. So that's my 3D printing spiel in a nutshell. And it's like the surface finish is super nice. The parts are dimensionally accurate, like within a thou. And it's temperature resistant, very high. So you can use it for timing belt pulleys or like the Krakens get up to like 130 Celsius. So they're very hot. So the covers that we have on them that shield the motors, if we were to print those in PLA, they would get soft and start to deform. So we have one material, that's the only material we print. We print that all day, every day. We never think about switching to anything else. Yes, it is a little bit more expensive, but the headache of not switching is, and for $50 a roll instead of $25 a roll of PLA, it's not so. More questions? More questions on 3D printing? Because I'm like really passionate about that. Yes. Point 4. Yes. Yes. Point 4. Point 4 in a bamboo. So everything on that robot was printed on a highly modified Creality printer. And in the carbon nylon, there's this ruby nozzle you can get on Amazon that's like $40. And it's amazing for abrasive filaments like carbon nylon. But in the bamboo one, I just use the hardened steel 0.4 mil nozzle. Stop 5 minutes.
What's that? Do you guys use that emphasizer?
Yes.
Yeah, what like control setting for
Depends what it is. If it's a timing pulley, 6 walls and like 35% control. If it's a cover, 2 walls and 40, 50%.
Do you guys like a standard controller?
Yeah, I have a profile for pulleys and a profile for everything else. And the pulleys one is like 6 walls, and whatever they default, the other one is just less walls. So just those 2 standard profiles. More questions? Yes.
So the one unique thing about your robot this year is you guys use the double-sided timing belt. Where do you guys get the idea to kind of do that instead of doing like gears and stuff to reverse these?
I've done those at work before for reversing applications. Yeah, it was one of those things that I was flipping through the catalog. I was like, cool, it's got teeth on both sides. So, yeah, we buy them from SDPSI. They're a small powertrain components company in Long Island. They're generally 2 to 3 days delivery, buy online, it's really easy. You get dinged with duty, that sucks. But they have all kinds of little gears and wheels and pulleys and stuff. We used to use them a lot more actually, but now we just print all our pulleys. Nobody buys pulleys, so we buy a lot less stuff. Yes.
How do you get away with not prototyping major mechanisms and larger things?
I think about things a lot. Basically, we rely on years of previous experience to know what's going to work and what's not going to work. There's no magic formula or presentation I can give that's going to impart, 2 decades of FRC experience. It takes a lot of time to know what's going to work and what's not going to work out of the bat without trying. So being a student of FRC history is a big advantage. Just look at old robots that were before you were around. Statbotics is a great resource that has statistical data on every FRC team for the last, 20 years. You can go back to the 2008 season And you can see that 1114 was 50% better than the second best robot ever. And go look at their robot and what made that robot great. Or flip to 2010 and see that Los Gorillas dominated the entire world until Einstein finds. And what made that robot great? Or, yeah, flip through to any year, look at the top 10, watch those match videos, think about what made this robot great. Why was it, top of the world that year? And yeah, look to the past for inspiration. More questions? Yes.
You tried for vision, or you decided that like you didn't want to investigate more time?
I have never looked at it. Limelight's pretty easy. You would have to give me a really, really good reason to want to look at something else. And unless there was a significant performance advantage to using photon vision over Limelight, there's not a real good reason for us to spend any time really looking at it. If photon vision was suddenly able to do 3D bot pose at 90 FPS with amazing accuracy, then yeah, let's go. We'll look at it and what it can, but it doesn't. So it's no better than what Limelight is, and Limelight's done. We just strap it on the robot and plug in. We don't have to do pretty much anything. So for us, we're always going to take the off-the-shelf solution. And if you look at, go to Statbotics, sort by EPA, look at the top 10 teams there, every single one of them uses Limelight. And some of them do have their own vision solutions for other stuff, but the majority of them are almost all using exclusively Limelight. More questions? You've been a wonderful audience. Thank you very much. I'll be around if you want to ask any more questions or have a look at anything. Thank you very much for coming out. It's been awesome. We'll see you next year.